Okay, all right. So again, there is a homework this week, right? It was out on the weekend, so it's not that long, but there is a homework. And the last question of the homework is not trivial. So anybody else look at the last question? The question that for the 551 students, that's a long question that's far from trivial. So give it a try, right? We'll grade that one fairly generously, but that is sort of close to practice. So that question shows you what actually goes on in a real-time calculation, right? And if you look, that question will take you through many steps. There's a lot of different equations you have to go through to solve that equation. So that's a challenging question, right? So it's not expected that you'll get to the final answer, but that's the whole idea too. Well, I guess there's a lot of steps in that question. So what's in there? There's sort of many steps you have to chain together for it to work. So it's not, it's likely that something will go wrong when you do all those kind of steps. But that's actually still not as complicated as what happens in practice, but it's getting closer. It takes you about 1 or 2 pages to do that question. Okay, so that's a question to try. Again, you're not expected to sort of do the whole thing. The midterm, I haven't finished grading yet. I graded some of it, looks reasonable. So I'm happy with what I've graded so far. I'll probably finish by this weekend. Sorry for a little bit slow on that. There's a lot of things going on here these days. Okay, so that's a midterm. Again, for the people who's eligible for the undergrad fellowship, please do apply. Right? There's no citizenship requirement for most of them. So we are trying to award 10. I think I have about 12 people who apply. So good for the 12 people who has applied, but still I want to see more. It's for people in this class who has not applied, please apply. All right, so that's those things. So today we'll continue with stability. We'll do some calculations for stability, and then we'll go into statistics. Okay, so we're going to sort of, again, up until now, we have been looking at the mechanics of wind power generation, not so much the operation. We've been looking at how does the motor work, basically. So after this, we'll go into the closer to the operations of wind power, which is what happens if things are stochastic, right? So let's continue with stability. So this class first, we'll still look at stability. So stability for us, for synchronous generators, is mainly about this one graph. Okay, so for us, stability is still fairly simple because what we have is we have the active power, the Pmax times sine delta, right? The sort of graph that we had. So you look at the angle of the generator, you have the terminal angle of the generator, and you look at the maximum power, where the power being generated looks something like this. So stability typically means where are you operating along this curve? Right? Where are you operating along this curve? So we want the operation to be somewhere here. So that's what we consider stable operations. Okay? When angles are small, when your angle is increasing versus the power you have to generate. We want to avoid operating very close to the maximum power generation. Okay? So a reason that, which we may not have covered last time is you want to avoid operating at the maximum generation is if you operate very close to the top and you have a small disturbance, what happens is this generator tends to oscillate, right? So think of it's a rotating machine. So basically it's like a harmonic oscillator. You have a rotating machine that the angle changes with respect to frequency, frequency changes with respect to power. You have a harmonic oscillator. If oscillate very close here, then this is considered an unstable oscillation because it can fall both ways. So you want to avoid operate sort of very close to the maximum power region. So most times you limit your situation stuff. Okay. So this is called a single bus infinite. This is called a single generator infinite bus model. Okay. So this is a single generator connected to a infinite bus. Right, so this is where we think of the grid again, as a infinite bus, right? So the circuit diagram is, this is your wind power generator, this is the terminal of the grid. So we're looking at power transfer along this line. So then it suffices just look at this curve. So this curve has been studied for the last 70 years. We sort of know everything that can possibly happen for a sine curve. We're very good at starting this, looking at this model. This model start having problems. For example, if you have more than a single machine. Right? So what is the infinite bus? The infinite bus you think about is the rest of the grid. Right? The rest of the grid is large enough that it's not impacted by your operation. So we can think of as a ideal voltage, just the ideal voltage component here. Of course, the grid, there's no infinite buses we have in the system. So what actually happens is the grid is you have lots of generators coming to the grid. Maybe you have some load here, right? This sort of more accurate representation. There's a more accurate representation. For this kind of representations, this graph no longer applies. There's nobody that's an infinite bus anymore. You just think about all the power flows here. And this is a much harder problem. Okay, we know much less here than here. So today's grid is mostly designed, assuming that from everybody's point of view, you're looking at an infinite bus, and you operate far away from your maximum power. That's the assumption we have. So if you ask people, why is the grid stable today, right? Why doesn't it fall apart? That's most likely the answer you'll get. As you look at, again, tight infinite bus, you operate very far away from the maximum power. You operate here, there's a lot of room to move around, okay? Right. So that assumption is starting having problems, okay? We're starting running to the assumption of everybody will see an infinite bus. That's a problem we're having now. So why is that, right? So what's sort of going on today that makes the infinite bus assumption not a good one? Okay, so this is not a very good assumption anymore. So what's changing today in the grid? Okay, good. So that's a good point, right? So one thing that makes this a little bit iffy is actually we're starting shifting all this operation closer to the peak. Okay, before what we had was, right, so again, think about the grid going forward. So right now we have very large generators, which they don't operate close to the maximum power. Like a nuclear generator is far away from that maximum power. Whereas you replace that by, say, 100 wind turbines, they'll all be each pretty close to maximum power, right? They'll be sort of, getting closer, maximum power. So we're starting off with it started to creep up along this curve for a lot of generators. Okay? So you're operating closer and closer to the max. There's less and less room to maneuver. Okay? So then this is not that good a model anymore. And again, today is what we have is we have a lot of sort of more microgrid coming. If you look at the microgrid, again, here close to us, we have the Arlington microgrid project. So if you drive about 40 minutes north, you'll see the microgrid. And in the microgrid, nothing is large. There is no large component. Everything is sort of similarly large. There's no infinite bus. There's everything of similar size. You cannot ignore stuff then. And then the sort of simple model starts to break down. And then the stability concerns becomes quite complicated. The math becomes much, much more complicated. So this curve is by no means easy. Again, if you take the graduate class next quarter about stability, you'll spend a good month on this. Just looking at what happens for one sine curve and the mining as much as you can out of this. But then if you look at sort of multiple things all interacting, again, we're not so clear what actually happens for all this bunch of things, right? So the model is, so the challenges today, one is we're operating. So today, we're just operating much closer to the limit, right? And So that's sort of the assumption that everything is small, all the angles are small, things like that, may or may not apply for today's systems. And then today we have things like microgrid. So there is no large component. So you look at microgrid, there's nothing large. So you cannot assume anything is infinite bus. Okay, so that's the challenge we have today. So in this class, so that's the challenges, but in this class, we'll largely still adopt this model. So our calculation will be based on basically this equation here. We'll look at a lot of what happens to this. Under this equation, what is the maximum power? How do you increase maximum power transfer and things like that? And keep in mind going forward, a lot of issues comes down to sort of whether you have multiple components. What happens there? So one, you're interested if we actually do sort of power electronics to grid simulations. It's pretty easy to connect three things together and trigger some protection, but some things are stable. We actually don't quite know why. So down in the EC building basement, we have this kind of experiments. And you need to be very careful when connecting several inverters together, driving a motor. You run into instabilities, we don't quite know why, we can sort of reproduce it. But again, this sort of basic theory is not great anymore in the situation, right? So that's something to keep in mind, okay? So again, for us, we'll look at this sort of simple single bus, the sort of one generator infinite bus, and we'll do some sort of calculations here. Okay, so that's the extent of stability we'll think about. In practice, again, there's a lot more things that's coming in. That's quite interesting. What's going on there? All right, so for us, let's do an example. So this is a typical example of question we'll see. So it tells you as well, you have a type 4 turbine connected to the grid through two reactances, right? So one is you have a transmission line, that's the reactance. You have a converter that has a reactance. And you're given two voltages. Right? And the question is, okay, if you have output power of 1 per unit, what is the angle? Compute the maximum power transfer. If the wind speed causes mechanical power to increase, okay, can you still operate the system? What happens if you want to increase the voltage? And basically, how do you, how much voltage do you have to increase? Okay, so this is a typical question of computing the maximum sort of power transfer in the system, right? So if you draw this diagram, this is what we have. We have a generator connected to the grid. And we have, so let me draw this with the reactances into it, the generator, some reactance to the grid. This voltage is 1 per unit, 1 per unit. This is 0.5 per unit. And we're saying this mechanical power input is 1 per unit. We want to compute things like the angle of the generator. Okay. So have everybody seen per unit? Has people not seen who has not seen per unit? Okay, so per unit is a way to say that we're too lazy to write all the units here. Okay, so for example, this is normally the voltage is in say kilowatts, right? The power is in let's say kilovolts. This is in megawatts. This is in ohms. Per unit says I'm too lazy to deal with all these units. So we're going to normalize everything by the correct unit. I just think of things as per unit. Okay, so that's a per unit system. Okay, for the people who have seen per unit, why do we do this? So everything in power is done in per unit. If you go in a control center, you will not see an actual unit. You'll see the sort of PU things. For people who have seen per unit, why do we make all this?
I think being at 1 unit is like the nominal value. So instead of looking at the custom numbers and just remembering what they're nominal, you'll see that it's 1.
Right. So the big reason is per unit tells us what is the right number to look at. Right? So saying a voltage is 100 kilovolts, you tend to think, okay, this Is this close to nominal? Is this too high? Is this too low? Am I offering correctly? So we just normalize everything to sort of the base unit. Then you look at this system and try, okay, yeah, this nominal 1 per unit, this nominal 1 per unit. Okay, this sort of nominal power I have for this. And look at you sort of standard setting. You don't have to think about, because there are so many units in your system, right? You have to, a lot of times you lose track of what is normal, what is not normal. So when you see per unit, this just means that think of this as actual units you can do calculation with. Right? Just we have divided out the nominal values for everything. Okay. Right. So again, that's useful because so is 1 ohm a normal number or not? How big are these? So again, you normalize everything. So everything is close to 1. The idea is all the numbers come close to 1. So per unit is actually quite useful in the system modeling. The values per unit quantities, right? So now let's say we want to compute the angle. Okay. So we have again this sort of line. We have x as 0.5 per unit. This is 1 per unit voltage, 1 per unit voltage. When compute the angle, right, of delta here, PM is 1.0 per unit. So the thing again to remember for synchronous generators is there's no losses in this line. There's no active power loss. So whatever is active power goes in here comes out at the other end, comes out as a grid. Okay, so PG is also 1 per unit. Right? We have no loss. And then we have PG as V out times VG divided by X sine delta. Then delta is sine inverse PGX V out PG. Plugging all those per unit numbers, you get this the sine inverse of 1/2. This is 30 degrees. Okay. So this is the calculation of. So you can think of this as a sort of nominal angle we're operating. Okay. So for people again for per unit, do we ever talk about the angle in a per unit term? No, right? We never talk about angle in per unit term because angle can be interpreted. So we're very good at interpreting angles. 0 is a small angle, right? Pi over 2 is sort of the maximum angle for power transfer. So angles are never talked about in per unit. Everything else is. So angle stays as degrees or radians. Everything else is per unit. So this thing you can think of under all the sort of normal conditions, this thing is 30 degrees angle. So part B says, well, let's compute the maximum power transfer. What is the maximum power I can produce? Okay, so maximum power, this happens at angle equals pi over 2, right? So P max is V out prime Vg x. This is 1 over 0.5, 2 per unit. Okay? So I can double the power output. So physically, what happens if I try to pull a power more than 2 per unit out of this generator? And physically, what happens to the generator if I try to do it? Okay. We'll slow down, right? So physically, you try to pull too much power. There's no power to give, right? There's sort of maximum mechanical power. We'll try to slow down. Turbine will try to slow down. And then the protection device in the turbine basically measures this speed. If it slows down by too much or speeds up by too much, we'll cut off the turbine. So that's the internal protection the turbine has. Okay. So it does this sort of measures the turbine speed. Okay, so this is clear, right? So PM increases to 2.1 per unit. Then we cannot, right? We cannot offer this operate without changing voltage. Right, so I need to change VL prime to operate something at 2.1 per unit. But yeah. So that'll be a breaker trip, right? So yeah, so your turbine gets disconnected from the grid. Then you have, so that you disconnect the turbine, then all the power is dumped through some resistor, and your turbine stops. So the way is, so you have wind turbine as your trip, then your pitch control will come in to stop the turbine from spinning, or should not generate power from wind. But there's some time until the pitch control completely kicks in. At that time, you dump all your power through that. Right? So the big, actually, this very stressful on the turbine. So the turbine in its lifetime cannot handle this many stops because it's a very sudden break in the turbine. So to brake as fast as you can for both overspeed and underspeed protection. So you try to brake as fast as you can, you dump all the power. And then so if so there's actually cyber attacks that tries the turbine to undergo this kind of frequent tripping. And turbine doesn't last very long. So it may last, tens of times in its lifetime. Right? So should not trip very often. Again, because these are huge machines that you don't want to stop. Right? So again, remember how big a turbine blade is. Stopping that thing completely within a few seconds causes a lot of mechanical stress. Okay? So it's a big deal if it trips. Okay? So you don't want to trip, but again, if you don't trip it, if the frequency keeps on, if your speed keeps on dropping, the mechanical of the turbine will be unstable. Then you have sort of blades falling off towers. That's kind of stuff. Okay? So you will trip, but that's sort of the last resort you do. Okay? So under frequency tripping is the last resort. Okay, so this is not stable, so you cannot put in 2.1 per unit of power into the system. Right, so to maintain stability of the system, then we have to increase the, for example, the V out. So here, part D says, well, now what is the minimum value of output voltage to maintain the stability of the system? So this is P max, is VL prime, Vg over X. We want this to be equal to 2.1 per unit. Okay? We want this to be equal. Okay? So again, we never get to change the grid voltage. This is determined by the grid. X you cannot change in real time. So all you can do in real time is changing your output voltage. And then you have some control in your converters of your voltage. Okay, so you set this voltage. So this gives us VL prime. This is 1.05 per unit. Okay, so this is the sort of the minimum amount of voltage you have to get to be able to output this power. So of course, we don't want to operate, right? We don't want to increase the minimum voltage. This will say again, your angle is at parity. So that's too large of an angle, 90 degrees too large of an angle. So what we often do is we say, well, you have to operate at delta equal to 60. Right? This is the angle we want to operate at. So this is VL prime, Vg. So we want VL prime, Vg x times sine 60 degrees. This is 2.1. So this is 1.21 per unit. Okay, so this is sort of the calculation we typically have. Okay, so again, this 60 degrees is still quite large in reality. Reality where will be very rarely do we see angle that's more than 45 degrees in this kind of system. Again, you don't want a disturbance to kick you over the hill. So 60 is still considered too close for comfort. Okay, so there's one sort of angle that's less than that. Any questions for this example? Okay, so yeah, so it's good to get familiar with type 4, right? So stability for type 4 is easy. For induction machine, it's much more complicated. We won't actually look at the equations. And then when after we do statistics, we'll bring it back to again to this kind of questions. For example, what happens in statistics is you can say, well, suppose the mechanical power is not just 2.1 per unit. Suppose there's now a range for this possible power, right? Then compute the angle or compute the voltage such that this whole range is satisfied. Or we can say that there's a range of possible mechanical powers. Compute the voltage such that we're okay under 95% probability. We have a lot of these kind of calculations we'll do. Okay, so even though the equation here looks very basic, we'll do this many times. Once we include other components, okay, so this will certainly not look that basic. Okay, so it's good to get familiar with this equation. All right. Okay, so let's do one more example, right? So this is active and reactive power calculation. So we'll do this. This is also similar to the homework that we'll have. That's this for this week's homework. So here we're saying, let's say we have a synchronous generator, again connected through a transmission line of different inductances. We're producing 1 per unit. The difference here is now I want to deliver 1 per unit of active power and 0.5 per unit of reactive power. And now let's compute both the voltage and angle. Right. So again, if you want to, right, so there's two equations, active and reactive power. So you need two unknowns. You need the voltage and the angle to be unknown. So this is the calculation we're trying to do. Okay, so what we want is, again, we have this line, we have 0.5 per unit as a reactance. The grid is always 1 per unit. Okay, so we never control the grid. And we want PG, here is 1 per unit. We want QG, this is 0.5 per unit. Okay, so we want this to happen. Let's compute what's V out and what's the angle of V out. Okay, so should we solve for the active power first, or should we solve for the reactive power? For this thing. Right, so the trick here is you basically need to set up a system equation, right? So there's not an easy way to say, let me solve for delta, then solve for V out, right? So there's two equations that are satisfied. We're going to write the two equations. And again, the way to solve it, so you're going to plot the two equations and look at when they intersect. Okay, so that's the, so there's sort of different ways we can solve this. Okay, so let's say, so we have the active power. This is V out prime Vg over X sine delta. Right? We need this to be equal to 1. So plugging all the numbers, we get V out prime sine delta. This is equal to 0.5. Okay, so this is one equation we have. Okay, you move X to the other side, you get this equation. So V out and sine delta, that's one equation. Now let's look at reactive power equation. Okay, so this is active power equation. Let's look at reactive power equation. So QG, this is Vg over X, VL prime cosine delta minus Vg. This is our reactive power equation. So let's plugging all the numbers here. It's 0.5, 1 over 0.5, VL prime cosine delta minus 1. Okay, so that's the equation. So putting things together, here we get VL prime cosine delta equals to 1.25. Okay, so this is the two equations we have. How do you solve these two equations? That has sort of two things multiplying each other. So for this problem, there's a trick, right? There's a simple trick. If you look at the two equations, what's the trick? You divide them, right? So written out this way, divide them. So this is a good trick to know, right? So if you don't do this calculation, if you stop here, then it's not obvious how you will solve this. Right? So often what people do is they'll stop here and then start, actually you could stop here and graph it. That's fine, that's totally fine. For this kind of problem, it's a bit easier to write this out. And then you can divide them. Okay, so this allows you to divide them. So if we divide them, we get VL prime sine delta, VL prime cosine delta. This is 0.525. Okay, we got this. So delta is tangent inverse of 0.4 and 1.8 degrees. So that's how you solve for delta. You can plug this back into whichever equation you want to get VL. Okay, and if both the equations work. Okay, so this is VL. Actually forgot to do this. So yeah, plug back into this equation. Get VL. Okay. Right, any questions about this problem? So the thing to remember here is you could divide the two equations. Okay, so when you do calculations, if you're very comfortable with programming, solving here is fine. When you do slightly more work, you can get to be sort of this form. And then you can do the tangent inverse trick. Okay. All right. Okay. So this is the another example of a very typical type 4 calculations that we have. And so the next is we can look at induction generators. So induction generators is very similar to synchronous generators. As again, you want to avoid operating very close to the peak. Right? You don't want to sort of fall off at both ways. You want to keep close to this side of operations. The trouble here is that the equations are more complicated. So this curve is not a very easy equation. So it's a more complicated equation to write down. So we're not going to do any of the calculations. You could repeat the calculations, but again, we're not going to do this just because it's not a very nice looking equation to do. But the idea is similar. Stay here and operate away from this. Right? Okay, that's the idea for all these generators. You have a range of operations, stay within this. All right, so that's the induction generator. Again, we're not going to do too much about it because we don't want to deal with that equation. Okay, so you could repeat the exact same calculations with this equation. The problem is you have to end up integrating this equation. And that integral is you cannot do by hand. Okay, so the computer software will do this for you. We're not going to do this. We're not going to try integrating that equation. Okay. So someone can. We're not going to try to do this. So lastly, we'll talk a little bit about system-wide stability. Right. So before, again, we're talking about a single generator, infinite bus stability, meaning stability to that generator. So now we're going to talk about system-wide stability. And the fundamental thing about system stability for power system, the thing to remember what makes a power system very special is the frequency gives you a feedback about the balance, load and generation balance in the system. This is the sort of the fundamental fact that makes the system work. Okay, so when we designed the AC system, nobody thought about this. We're trying to get higher voltage in the system. But now the AC part of the system really is about having this feedback signal. So the frequency in the system gives us a good feedback about the imbalance of energy. So frequency is a feedback of sort of energy balance. And this is quite rare. In most other systems, you don't have this kind of feedback. What this allows you to do is to measure your own local frequency and understand what happens for the entire system. Okay, so for example, we can measure our frequency. We'll know something about the entire energy balance of the West Coast. There's quite a bit of information in a local frequency you can measure. That is very, very rare in this kind of system. Okay, we're sort of locked into this. Again, when Tesla decided to do AC. Nobody thought about this, when we start building AC systems. Then it's recognized you have this kind of feedback. This is quite rare. So this, for example, does not happen in the internet. One part of the internet having outage or one part of the internet having overload does not really impact other parts. This does not happen in traffic, right? So traffic jams are very localized phenomena. It's very, very rare to have a system where you have a local variable you can measure that tells you about the global state of the system. The entire stability of the system is designed based on this insight. You want to measure this. Okay, so let me say a bit more about this. We don't have sort of the right tools to look at equations, but again, when we think about frequency, right? We think about the 60 hertz and a bit more than 60 hertz. How is this frequency actually measured in the system? So what does frequency mean when you go and measure it? Okay, so frequency basically assumes the system is a sinusoid, right, with some frequency. So the way you measure it is you measure the zero crossing of this sinusoid. Okay, you count when it crosses zero. You put a sensor in the wall, you count this, and you got a frequency. But nowadays, people are getting sort of much more advanced in this. As instead of just measuring a single number, so is it 60, is it more, is it less? People start to measure the time domain choice of the exact voltage waveform that you have. Okay, so we have high enough sampling capability to measure that. There's a lot of activity in mining information out of that entire waveform. Okay, so if you think about what machine learning is doing, people are feeding that with a lot of machine learning output to say, right? So because this is a feedback signal, if I know more than just the frequency, right? If I know the time domain waveform, do I get more information about this? Right? So one question people have is, for example, I measure frequency here. I know the power imbalance for the entire West Coast. That I get by this aggregate amount. Can I tell whether the imbalance, let's say, is in California or Oregon? So that's a question people have. If I just measure the Seattle frequency, I look at the time domain waveform, can I tell where it is? Can I tell this kind of thing? Right? Can I tell, is it in Canada? Is it in California? So people are trying to figure that things out, those kind of things. So those kind of local measurement is very, very powerful in the very, very rich information in the power system. We don't quite know yet what happens when you look at the time domain, but you're interested in signal processing or in machine learning, there's a lot of work going on there. You sort of take the highest sampling frequency you can have, go measure it, and look at it. Can I tell different things? And so here, we'll take a more aggregated viewpoint and just say this is the frequency. So this is actually not a, so this, you need to average this across a few measurements to get accurate reading between zeros. So think about this frequency being a measure that's in the sort of tens of millisecond time scale. Right? I need to wait for 10 to 100 milliseconds to get accurate frequency. So this is not quite at the real time, but pretty close to that. So we're talking about sort of hertz, tens of hertz for the measurement time scale. Okay, so for frequency allows you to do is really this defines whether the system is stable or not stable. Okay? So your goal as a power system operator is to make sure the frequency looks like this. So frequency will start to drift away from 60 hertz because there's some disturbance in the bit. Anytime you turn on a light, do anything, there'll be small wiggling like this. You want to make sure this comes back to 60 and not do this or this. Right? It doesn't do one of these kind of things. So the experiment I talked about where we connect inverters, things are unstable, we see something like this. And then something trips, right? So we have protection that trips. So that doesn't burn down the building. But this is, we don't quite know what happens here. So you want to make sure you operate like this. And this range is quite small. Okay, the tolerate range before we take sort of very, so the range you want to keep this in. This range is typically sort of plus minus 0.05. So it's a very, very narrow range you want to keep the system at. If it goes out of that range, we don't know. If it goes out of that range, this may happen, we're not quite sure. So we simulate the system quite extensively within this range, make sure it's okay. Your job as operators, make sure it doesn't go out of range. Good. Yeah. No. So that's the US number. In Europe, it's a bit higher, but still it's a tiny range. It doesn't vary beyond. So US is quite small. Europe, I think, can go about 0.1 Hertz. So a little bit higher. But again, this is so frequency is something you look at. You look at very closely. So what happens when you have this kind of variations, right? So how do you make sure this happens? So how do you make sure, for example, you can go back to 60 and not do something unstable? So what do you need for the system to be stable? What property or what do I need to do in the system? So I have some kind of feedback control. I need feedback control. So I need to be able to measure frequency. As I can do that. But what else do I need? I need some flexibility, right? I need some headroom. I need some operating headroom for this to happen. Because if everything was operating at the limit, and then suddenly I increase the load, well, there's nothing I can do. Right? That's not specifically what this is. So for this to happen, I need some operation room. I need some headroom. I need some flexibility in the system to absorb this kind of disturbances. Okay, I need things to be able to change according to my feedback signal. So this requires flexibility. Okay? This requires flexibility for this to happen, right? I need something that can absorb the disturbance. So how do you achieve flexibility? For example, so load typically doesn't provide flexibility. So how does a generator provide flexibility? What is the easiest way to operate a generator such that you have some flexibility to? Right, so don't operate very close to your limit. Right? That's basically right. That's the simplest way to ensure you have flexibility. Stay away from the maximum minimums. So for wind power, this typically calls something of a delta control. Okay, so delta control is something that says if this is your maximum wind power you can provide, have some slack, have some flexibility for wind. Don't offer very close to your maximum in case the system wants flexibility. So it's called delta control because there's some delta you maintain in the system. Right? So wind, the problem with wind, this for maximum possible goes up and down. So this typically shows up to a fraction. Operate 80% to your max. Okay, so give some headroom for the system to move you around. Okay, so that's your maximum power capability. Or right? So one issue with this kind of with wind is because this is not exactly stable. This is not exactly a straight line. A lot of variability in wind. So another way to provide flexibility in wind is to say, let me operate below the actually sort of the lowest possible. So this is another way to operate wind. It is to say this is maximum possible instead of moving up and down all the time, which actually again creates disturbance in the system. Let me just operate here, where I can appear as a conventional generator. Right? I can give you a steady output. Right? I can give you a steady output. So for wind, there's delta control. There is something called sort of balance control, where you stay below your operating possibilities. Okay, so these are possible. These are things you can do. And these are some things, sometimes we do this with actual generator. For example, especially delta control. This happens for every generator. So no generator will operate as max. Every generator will have some headroom to move around. And this is much more problematic for wind than for a conventional generator. Can I think of what? Wind turbines complain no end about this control. Conventional generator is okay with this. If you operate a wind turbine, you do not like this kind of delta control. Think about why is that? Why would a wind farm not like being controlling this type? Okay. No, let's say that's not the issue. Let's say you don't have that. But think of from economic perspective. Think of money making perspective. If you're wind, if you're lobbying, let's say for a wind farm, your number one job is to get rid of this. So how is cost calculated for a wind farm? What determines the cost of power generation? Are there fuel costs for wind? No, right? So for a conventional generator, if you move off from your maximum possible generation, use less fuel, so you have less cost. Right? So you're okay with that, right? I'm generating less, but my cost is less. I don't need to consume fuel. For wind, there's no operational cost, or very little operational cost. Most of the costs come in your capital cost, right? So I build to the maximum, so I spend money to be able to generate this. Now you tell me to back off. There's no saving. Right? There's not like I save on fuel or I save on different things. As I'm losing opportunity cost. I could have been generating a maximum. Right? So people pay me on what I generate, not doing this kind of delta control. So this, you lose money if you do this for wind. Anytime you're not at your maximum, you lose money. So for wind, there is not a point of break even where the fuel is too costly, you don't want to generate more, things like that. For wind, if you can, you generate to your maximum. That's where you get money. Right? So all your costs is basically upfront capital investment cost. Yeah. So wind does not like this. Okay, so that's where you lose money for wind. And a 10% delta control, you lose 10% of possible money you can make out of this thing. So wind complains to no end about this. Right? And this is not, you want to incentivize wind, that's perhaps not the best way to incentivize wind. So that you spend all this money, you spend hundreds of millions of dollars building this big farm, but only offering 50% of it because I need flexibility, right? So any ways of improving this? Right, exactly, yeah. Yeah, they all have the same issue. But all these things are capital intensive, almost zero operation cost, right? And they're variable, right? So if you tell them, the goal is always to offer as a maximum possible output, right? Power point. So how will you deal with this? This is the actual question we have. You need flexibility. You always need flexibility. Otherwise, the grid falls down. But then we want to incentivize this kind of renewables, which almost always have zero, right? By definition, in some sense, they have zero operating cost. So how we deal with this? Any suggestions?
Like government subsidies that can like have deals with all of the renewable generation owners.
Right. So before when was starting from, let's say from the 2000s, basically the way is you can operate away from the maximum. I will pay you as if you're operating your maximum. This is government subsidy, right? Actually, your actual payment is not the actual power generated. We'll make this up to you for this gas. That has run its course. That got too expensive. Right? So that basically we all paying for. Right? Each of us pays for that. So that has people don't like that anymore. So.
There was the whole colloquium about this. One of the things that was mentioned is the running water treatments, running different phases, different times to make sure that the power consumption was available. Things that you can't run.
Right. So another right now, instead of just paying wind, now it's like, can we shape demand? the big direction, there are two big things that we're trying to do. One is can I shape demand to match with, right? Instead of asking when to provide flexibility, can demand provide flexibility? So people are saying like water treatment plant, pool pumps. When do you do heating and ventilation? You have some flexibility. Your data center, do you have to run, all this, deep learning at the exact same time? Can you wait a few hours? All those kinds of things, right? Can you shape demand? That's one area. Another area is storage. It's always talk about if I have storage, I can do better than this. I can provide flexibility. Okay, so the two big sort of research topics we have nowadays is can I shape demand? The problem is when people listen to you, you can try shape demand all the much you want. If people says no, then what do you do with that? Second is if I put in storage, can I help? Can the storage help? For example, Professor Kirshen's sort of big research topic is if I add storage, what does this curve look like? Again, no simple answer for that. It's not obvious how much storage you need. And so the question people want to answer is, let's say I have 100 megawatt or a gigawatt wind farm, how big a battery do I have to buy? Right, for that to look like a conventional power plant. No easy question there. It's not obvious. Right? So that's we'll look at statistics, then we'll look at storage. So we'll try to answer some of these questions, making a lot of simplifying assumptions to answer this question. Okay, so that's something to keep in mind. Really, the challenge of wind power operation is not can I make a better turbine? What do I do? It wouldn't look like this. What exactly, how do I deal with this? Okay, so it's a good time to take a break. Let's go to break until 9:32. Then we'll switch gears, we'll look at the probability and statistics. After that, we'll come back to this point. Without storage, how do I make sure this looks better? Okay, all right, so let's look at statistics. Okay, so statistics, what this really is about is sort of very non-rigorous view of probability, of a single probability. So for folks who are here who has not taken probability, who has never taken a probability class. Okay, all right. So the way we'll think about this is the following. So if you look at wind, so we look at wind, we think about wind as well. We say wind is variable. So let's say this is time. Let's say wind speed or power. Let's say speed first. It looks something like this. Right? So this is quite stochastic. We think this is quite stochastic. There's a randomness in here. So this is actually a hard thing to think about. Because if you look at this kind of trace, what this is actually a stochastic process. It's a function of time, right? This is a stochastic process. This is actually a function of time. What is even more tricky about this is, remember that we almost never have a single turbine, as we have a wind farm. We have many turbines together. So what actually you need to look at is, let's say you have a farm, just more evenly spaced. What we really want to talk about in terms of stochastic things for wind is we want to talk about sort of a probability or as function of space and time. Okay, so that's really sort of what the true probability or true statistics we want to look at is. For example, given this turbine at this particular time, what is the wind speed? This kind of thing, right? We want this kind of understanding. Okay, so really there's a probability that is a function of both space and time. So that's that is a difficult thing to study. It's a difficult thing to study even in sort of very advanced probability. Because things in time is called a stochastic process. Things across both space and time, there's sort of a spatial stochastic process. And then you start to look at the correlations between different forms, correlations across different times. those becomes, even describing that is challenging. Even describing that is challenging. Another challenge we have is wind speed is really a real number. Right? Wind speed is a real number. So we have to think about the probability of a real number happening. Okay, so the one challenge is we're looking at space and time. Another challenge is that the fact that we're looking at a real number. Right? So, or power is a real number, is a sort of continuous number. So, we have something described because there's infinite number, right? It's called uncountable number of real numbers. How do we describe that? Okay, so, and really, if we understand it, how do you talk to somebody, like a policymaker, right? How do you tell them what I want to do is describe a process as over 2 dimensions, and now it's drawing a real number out of it, right? So that's a lot of information. That's hard to think about. Okay, so we'll not get to this one. Okay, we'll be far away from this. This will take us many classes of actual probability and statistics to get to actually describing this kind of thing in detail. So what we'll do is we'll start with the simplest model, and then we'll eventually build up to what happens when you have sort of multiple wind farms. How do you think about going from one wind farm to multiple wind farms? Before that, even within a wind farm, when you think about how do you think the fact that there is a time variable going on? Okay, how do you think this is a function of time? For example, for wind, for right now versus next minute, what's an hour from now, what's a day from now, there's a factor of time there. Okay, so first, right? So first we learn how to think about in time, then we learn to think about in space. Okay? But when we start, we'll think about this neither in time or space. We'll also pretend there is not a real number for wind. Okay? So we'll describe all these things. Okay. So let's deal with the fact that alpha is a real number. The problem is anytime you have alpha that's a real number, you cannot store in a table. Okay, that's the issue you have. Because so first we want to store things in a table. Right? So we have alpha that can be a real number. It's hard to say what is probability of the wind speed being 10 meters per second. Well, being 10 point something per meter per second, 10 point something, right? So you can't store in a table. The first approximation we'll make wind speed is discrete. Okay, so this first approximation we'll not think wind speed as a real number. We'll think wind speed only comes in a bunch of discrete values. For example, things like 8 meters per second, 8.5 meters per. So in terms of meters per second, so something like 8, 8.5, 9, 9.5. We'll think of this in discrete values. We'll think of this as in discrete values. What this allows us to do is to assign a probability to each of these values. Okay, we'll assign probability to each of the discrete values. Okay, so this is what we think of wind speed at. In practice, what's happening is if it's something, right, if it's not exactly this number, you assign it to the nearest number. Okay, so that's the way we think about it. This allows us to potentially store things in a table. Okay. So that's one approximation we'll make. Second, we will think so let me write it. So each time have a realization. Right, so we'll have a realization of that. So what this means is, instead of thinking wind as something evolving over time, which is hard, what we think about is at each time when I take a measurement, I get one of these values. Okay, so that's called a realization. Okay, each time I measure, I get one of these values. Next time I measure, I get one of these values. So we're not gonna treat time as something with sort of an arrow that's going forward in the future. We're just thinking of as we go through time, I got multiple samples of wind speed. Okay, so each time I measure, I get a sample. Well, disregard the fact that time is evolution, all that. Okay, so what actually happening is to a first approximation, when we look at wind, we'll think there's a big table of value you can draw from. Each time I measure, I pick one value out of this table. Okay, and that's my realization for it. Okay, so the way you can think about this is, so let's say you have discrete. So these are the discrete values, again, as an example, right? And each time when we measure the speed of wind, we get, let's say, one value out of this table. Okay, so here I got this value, I got this value, got this value. Okay. So there is no notion of things evolving in time. It's just that we have tables, we're drawing numbers out of the table every time we measure. Okay. Right. And then the next assumption we'll make is each of this draw is independent. Okay, so the fact that I measure the value here does not mean next time I'm more likely to measure closer here, something like this. Okay, so next assumption we'll make is these drawing are independent. The sampling is independent. Okay, so this is our sort of very incorrect approach to modeling wind, but this is how we will think about it. Okay, so I'm looking at a bunch of values, and now I'm looking at, okay, which number do I draw? We're going to pretend there's no correlation. Okay, it's not like, we don't think the past will influence the future. We're drawing independent samples from a giant table. Okay, so that's our model, mental model of wind for now. Again, the benefit of this is, one, I don't need to talk about real number. I can store things in a table. The benefit of these two is I don't need to tell you how things are related. All I need to tell you is if I draw each time, what are the possibilities of getting, what are the probabilities of getting these values? Okay, we're going to ignore everything else. I think of this as our random model. Questions for this random model? Okay, yeah, go ahead.
I think that makes it not realistic to expect.
Right, what makes not realistic is the past, the future depend on the task. Right, wind is not going to go from very low to very high immediately in the next, in a second. There's a lot of correlations from the past to the future. Again, also is to actually make calculations, you want to make those things accurate, you have discretizing a very fine map. Right? So that sort of defeats the purpose of having discrete values. And so those are not super realistic. But the biggest problem coming from the fact we're ignoring how past influences the future. Okay, we're completely ignoring that. Right? We're going to think of each draw again as independent. Forget about what you have seen before in the draw at this time. That's not realistic. That's not how things work in nature, right? The fact that we can predict weather with some accuracy is because future depend on the past. Right? But for now, again, ignore all that. This is our probability model. We'll get there, but not for a bit, not for a bit. Okay, so this is our probability model. And what allow this us to do is we can just continue and go measure each time, right? So which value do I get? Next time, which value do I get? What you can do, this allows you to do is you build up this kind of frequency table. Okay, so what you build up is this kind of frequency table, because what you do is you go measure across a year. Okay, every time, every hour, you measurement, you look at, okay, what value do I get? What value do I get? Then you write these as sort of how many times do I get a particular value. Right, this is how you build up this kind of frequency table. Is value of 0, 400 hours out of the year, I got a value of 0. 12,000, okay, so these numbers are made up to be round numbers. So 1,200 hours a year, I get a value of 0.5. This kind of value. I can build up this table. Okay? All right. So this table starts to look at something. Right. So this is a histogram, and now start to look something like a probability, like a probability distribution. Okay. So if you look at this table, You'll say, well, over a year, most likely I'll get these two values. Right? Very unlikely I'll get the tail. It allows you to build out this table. But to get to this table, we're making all those assumptions. Okay, we're making all those assumptions that value only happens here. The weather, right? So there's no correlation between say measuring 0.5 and measuring 1. All these are ignored, but that allows us to build this table. And this table is useful because at least at the yearly horizon, it tells us how fast the wind is blowing, right? How fast wind is going. It'll tell us this site is probably not very good for wind turbine because the wind speed is very low, right? So for if the speed is concentrated here, will be better site for wind turbine. And so that will allow us to get from this kind of information. Right? All right. Questions? Okay, so again, this right now we're going to think about probability. We're going to think about randomness in a table. There's values. There's how likely you'll get those values. Okay. So that's our model. And what we want from this table, one is to look at it, get some intuition. That's very useful to plot. Second is we want to do calculations based on this. For example, if this is wind speed, then what is the likely wind power? Right. So we want to do this calculations. We also want to talk about things like, what is the average wind speed? What is sort of standard deviation? How big is the spread? We'll talk about, what is average wind power? All this kind of things. Okay, so once we have this kind of statistics, we can compute other quantity of interest and then talk about average things. Right? So again, if you, for wind power, you could talk to a policymaker or you may talk to grid operator. You don't really show them this, right? You show them some numbers you got from this table. Okay, so we'll work with this kind of table to get numbers. So technically, the name for this is called a discrete distribution. Okay, so there's a name for this. This is called a discrete distribution. And then it's called discrete distribution because there's only finite number of values. There's a sort of finite number of values. Each of them is assigned a probability. Right. So there is sort of finite number of values. Each of them models events. Right? So for each of these values, we assign probability. Right? So each value is assigned probability, and this probability is just like flip a coin, right? Half-half, this kind of thing. So there are some constraints on this probability. Okay, there are constraints on this probability. There must be positive numbers. Okay, the probability must be positive, and they must add up to 1. Okay, for this to make any sense. Okay, we cannot have negative probabilities. They have to add up to 1. Okay. These values could be negative. There's no constraint on what these values can be. They can be whatever you want. Just the probabilities has to be non-negative, has to sum to 1. Okay. So this is our model. Any questions about this? Okay, so this is called a discrete distribution. So again, a distribution is a table, right? So what this discrete distribution allows you to do is a table. What it tells you is, right, you have a value, let's say wind speed, W, wind speed value of W, and then there's a probability. This is, for example, PI. Okay, so there's some value of wind being WI. There's a probability of PI. Okay, so this is the distribution, this huge table given to you. This by itself is useful, but not often not the anything what we want to report. So we need to, in addition to talking about distribution, we need to talk about random variables. So there's another. Who has not have heard of random variables? Okay, so for people who don't remember what random variables are, okay, so a random variable is not random, it's not a variable. Okay, so that's again the very bad choice of names for random variables. What random variables do is the following thing. A random variable so this is called sort of RV, a random variable, as a function that maps the values to some number. Okay, so this is a random variable. As a distribution, you have a bunch of values. A random variable takes these values, assign some number. And this is a very useful way to think about what do you want out of this table. Okay. So for example, what are random variables that we care about? A random variable could be the average, or let's think about the right. So random variable is you assign to some number here. So for example, random variable can be the original or the original distribution. You just assign the value to yourself. That's fine. That's fine. What random variable is, this can be the one power. For example, what this does is you take wi, you assign the value to wi cubed. This is roughly how one power works. Okay, right. So I can go from speed to power. This is a function takes a value assigned to another value. Okay, this is what happens to this function. So this is a perfectly good random variable. This could be sort of, random variable could also be the sort of failure of a turbine, right? So how this will work is you take sort of Wi larger than, so how will compute failure? If let's say a turbine, or actually, let's see. Okay. So operating range of a turbine. Okay, so how will you sort of assign this to a number? Well, here you can do is you can assign number 1. Let's say if so what this does is, right, so let's say my turbine is on if the wind speed is between 5 and 15 meters per second, it's off otherwise. So this allows me to go from this table to define another number, okay, define another function of interest. Okay, so random variable is just this kind of function. Okay, so from the basic table that has all the information, we can do this kind of different calculations based on this basic table. Okay, so that's why we'll sort of talk about random variables. We'll talk about what is a random variable, what are different things associated with random variable. It just, out of one probability distribution, I can compute a lot of different things. Okay, any questions about this? So things will become sort of more clear as we go on, but this is sort of the idea we have. Any other? Okay, so this is the random variable, and again, to be clear, a probability distribution, the discrete distribution is a table. The table has 2 vectors, and they have the same dimension. Okay, so we have is value and probability. Let's say WK, there are K of them. Each of them will associate P1, P2, PK. They have the exact same dimension, right? This table has the same dimension. Each value has to be associated with the probability. There has to be some probability of getting the value here in this table. And the probabilities are required to be that Pi is larger or equal to 0. And sum of Pi has to be 1. for it to make sense to be a probability distribution. Okay, so this is our probability distribution. And then in general, these need not to be numbers. Okay, right? When you flip a coin, it's head or tails. So this doesn't have to be numbers. For us, this will be numbers. Okay, so but in general, for this values or events doesn't have to be numbers. I guess we require this to be a number because that's in wind, we typically think of this as numbers. Okay, so the idea to have in mind, these are wind possible wind speed. Okay, so we're going to associate a number to each event, and these are the possible wind speed. Okay, for each wind speed, we'll associate a table. Right? We'll give it for each of this wind speed, we'll give a probability. So the good thing about a distribution is a distribution contains all the information. Okay, what distribution means is this is both the value and the probabilities. Okay, so it contains all the information you ever want. Right? What are all the possible speed? What are all the possible probabilities associated with each possible speed? Okay. Any questions about this? What a distribution is? So why, in reality, in practice, we almost never talk about distribution. Why is that? So as a power system operator or as a wind operator, you actually never look at a distribution. We never look at it, when we talk to people, we don't say, oh, this is a distribution. Let me tell you what are the possibilities. Let me tell you what are all the associated probabilities. The reason is this is often too much information. Okay, this is a huge table that contains everything, okay, right? Especially if you have a wind farm, there are many wind turbines, there's too many numbers to make sense out of it. Okay, so distribution contains all the information, but it's not that easy to interpret. Okay, so often is what do you want to do with the distribution? What does it tell you? And now that I collect all these numbers and go and look at it. Okay, so distribution does have all the information. It just is very hard for people to understand. And so that's why when we have a test, right? We say when we have a class, we say what is the average GPA for this class. We say what is the standard deviation. You're not showed a huge table. Say this is all the possible classes in the university. These are all the grades people ever got. Go look at it and try to make sense out of it. Right? So you need to summarize. You need to summarize this distribution. Okay? You cannot just give people all this information and say, do something with it. Okay? So a statistics is a summary. It's sort of some description of the distribution that I don't need all these values to compute. I'm not interested in looking at every possible thing that can happen. I want a summary out of it. Well, the easiest one being things like, right, what is the average? Right, what is the average of the distribution? What is the standard deviation of the distribution? What is there's many things. What is the sort of the probability, 95th percentile, this kind of thing, right? So we're going to make a distinction in this class between the average, right? Between the distribution and the statistics of one. Okay, so when I say distribution, I mean everything in a way. Right? I mean sort of every possible, all the values, all the probabilities. When it's a statistics, usually means a single number computed based on the distribution. Okay, so that's the distinction we'll make. Again, in practice, we often is communicated as the statistics. not a distribution. We very rarely communicate to people through a distribution. We're much more likely to talk about, okay, this site has the average width of this speed. This site has the average width of the other. Okay, any questions about the difference between the two? Okay, so a big part of scientific communication is trying to get people to understand. So eventually we talk to operators and policymakers, how do you communicate stochastic things? How do you communicate random things to people, right? So without, just telling them this is all possibilities. So we will not make any formal definitions. We'll look at a sort of a good example that shows all these statistics that's just not trivial. Okay, let's do this. Okay. So let's say I have one site. This is all the possible speeds. These are all the possible probabilities here. Okay, so let's compute the average. So first of all, let's compute the average. So what's the average of speed? What is the average speed? So I haven't defined it yet, but sort of fairly obvious. Right, so the average speed as well, each of them is, 1/3 likely, right? 1/3 probability. So this is just 0 plus 10 plus 15. Right, this is the average speed. So this is 8.3. So this average speed, quite simple. What is the average power? Let's assume 1 power. So ignoring constants, 1 power is roughly speed cubed, right? What is the average power? How do I compute the average power? Do I just keep that number? Should I just keep 8? Is 8 cubed the average power? No, right? So that's the one pitfall people have. If you think, oh, the average speed is this number, maybe the average power is just keep the average speed, right? Or just keep this. This actually happens a lot. This happens a lot. If you read a lot, again, for things like even in, fairly well-known newspapers and publications, they will do this. They'll say, okay, this is the cube. Let me just keep this and get a number out. Right? That's not how you compute it. The way to compute a cube is you have to keep all of these, keep the probability the same, and then average out the power here. Okay, so that's a statistic, right? So that's the average 1 power. So this is average power is not average speed cubed. Okay, that is a wrong calculation to do. Again, this is a pitfall that many people fall into. There has been wind farms picked because people did this calculation. And this sort of obvious and wrong calculation to do. What we should do is we should build this again, right? So when we talk about this kind of function, we'll build up this kind of random variable. The function applies to this value. It does not apply to the probability. Probability stays the same. So we need to build up another table. Okay? So we need to build a power to probability table. Here is we have 0, 10 cubed, 15 cubed. This is 1/3, 1/3, 1/3. Okay, so this is the table we have to build. And the average power will be divided by 3. This will come out to be much larger than this thing cube. That's a much larger number than this cube. Okay, so one thing to be aware in statistics is statistics are all derived from the distribution. But don't try to link one statistic to another statistic. Okay, you have to go back to the same original distribution to do all this kind of computation. Any questions for this example? Okay, and so don't fall into this kind of trap here. Okay, speed is related to power. The basic idea is why don't we just compute average speed and compute average power? So that's not how things work. Okay. Okay, so we'll stop here today. I need to run a little bit early for this class. So let's stop here today. Next class, we'll go to some more formal definitions. We'll define, we should write down equations, how to do these computations. For this idea of the classes, right? For this section, you'll be always given this kind of table. You'll be asked to compute something. Again, the main thing to avoid is to do this kind of calculation. Okay, don't do this. Then it'll be fun. Just sort of work with the values and look at the probability. Okay, so with that, see you on session.